All right, welcome to this explainer. Today, we're opening up what I honestly consider the ultimate coding toolkit, data structures and algorithms. A lot of times when people hear DSA, they immediately think of these dry, heavily academic subjects that are totally reserved for stressful university exams. But actually, scratch that. It's entirely the wrong way to look at it. Instead, I want you to think of data structures and algorithms as the core, foundational tools that allow software engineers to literally build our modern digital world. I'm incredibly excited to guide you through this today, because mastering this stuff doesn't just make you a better coder, it completely transforms the way you approach and solve problems.
Okay, let's dive into this. Have you ever wondered why companies like Amazon, Google, and Facebook prioritize DSA so heavily in their hiring process? I promise, it's not just to torture applicants. It's because, at the massive scale they operate, most of their engineers' time isn't actually spent just writing basic code or, learning the newest framework. Their time goes into developing deeply optimized algorithms to achieve results at a staggering scale. Think about it. When millions of users hit a server at the exact same time, a poorly chosen algorithm can literally crash the entire system. So, here is our roadmap for today's journey. First, 1. Why learn DSA? Then, 2. Linear versus nonlinear structures. Moving on to 3. Measuring space and time. Followed by 4. Big O, theta, and omega. And finally, 5. Analyzing recursive algorithms.
Section 1. Why learn DSA? The ultimate payoff.
Understanding the why here is absolutely crucial. This toolkit is essentially the bridge that transforms you from a regular computer science grad into a truly exceptional engineer. The benefits are just massive. First off, it helps you crack those tough scenario-based interviews. Interviewers don't just ask about coding syntax. They ask real-world questions, like exactly when to use a binary search, to test your fundamental problem-solving skills rather than just your framework-specific knowledge. Plus, knowing DSA gives you the power to optimize your code so it handles high server demands smoothly. It lets you organize incredibly messy real-world data and fosters the exact kind of out-of-the-box innovation needed for highly scalable solutions. Basically, frameworks come and go, but these core principles, they're forever.
Let's move to and see how this builds. Section 2. Linear versus nonlinear structures. The organizational bins.
You can think of data structures basically as organizational bins for your messy datasets. The right bin makes finding your items instantaneous, the wrong one means you're digging around for hours. We generally divide these bins into two main categories, linear and nonlinear. Linear data structures arrange elements sequentially, so every element is attached to its previous and next neighbor, meaning you can traverse the whole thing in a single, straight run. They're super simple to implement, but they don't always utilize memory in the most efficient way. Nonlinear data structures, on the other hand, are hierarchical. They involve multiple levels, and you definitely cannot traverse them in just one go. While they're a bit more complex to build, they use memory highly efficiently and are absolutely perfect for representing complex real-world relationships, like social networks or vast telephone grids.
To make this a bit more concrete, let's look at two really common linear structures. First up is the stack, which operates on a last-in, first-out basis, or LIFO. Think of it exactly like a physical stack of books. To safely get to the bottom book, you have to remove the last book you placed on top first. Then we have the queue, which operates on a first-in, first-out basis, FIFO. A great real-world analogy here is just a line of people waiting to get on a bus. The first person in the line is the very first person to exit the queue and board, while the last person to arrive just waits their turn at the end.
All right, Section 3. Measuring space and time, the efficiency metrics.
And this brilliantly illustrates our next point. Now that we know how to store data, we really need to shift our narrative from how we store it to how well our program actually runs. Notice how, as our input size n grows on that bottom axis, the running time shoots up depending entirely on the chosen algorithm. That O of one line at the very bottom, that's a flat best-case curve. It takes the exact same amount of time no matter how much data you throw at it. But check out those red and orange curves, like O of n factorial and O of c to the power of n. They shoot up almost vertically. This visual demonstrates exactly why we need hardware-independent analysis. As your inputs grow, a terrible algorithm running on a multi-million-dollar supercomputer will eventually be beaten by a great algorithm running on a standard, basic laptop.
Now, while time is definitely critical, so is memory. Space complexity is the total amount of memory consumed by an algorithm from start until it completely finishes execution. It's simply calculated by adding the auxiliary space, which is just the extra temporary workspace an algorithm uses, together with the memory required to hold the actual input data itself. If we break that space down even further, we see it goes to a few specific places. There's a fixed part, like instruction space, which is literally just the memory occupied by your compiled program code. Then, there are the variable parts that grow right alongside your problem size, things like data space, which holds your dynamic data structures and variables. And finally, there's environment space. This is the memory used on the runtime stack for every single function call. It holds things like return addresses. And spoiler alert, it's incredibly important when we talk about recursion in just a minute.
Section 4. Big O, Theta, and Omega, the language of efficiency. So, we have these concepts of time and space, right? But how do we formally talk about them? Well, developers use asymptotic notations. It's basically the universal mathematical language for evaluating scalability. Let's clearly contrast the three main notations side by side. Big O represents the upper bound, the absolute worst-case scenario for how an algorithm is going to perform. Big Omega represents the lower bound, the absolute best-case minimum time required. And Big Theta? That represents a tight bound, meaning the algorithm grows at a highly predictable, exact rate where the upper and lower bounds basically match. Now, a very common beginner mistake is assuming Big O is the only metric that matters. But knowing the best case and average case limits is just as vital for real-world optimization. Let's look at a concrete example, using a simple linear search just to see why having different bounds really matters. Imagine you're searching for a specific number in a huge list. If that number happens to be the very first item you check, well, your algorithm stops immediately. That is your best case, big omega of 1. But what if the number is hiding at the very end of the list, or maybe it isn't even there at all? You have to check every single element. That's your worst case, big O of n. It's the exact same algorithm, but completely different bounds, depending entirely on where the data is hiding.
And finally, Section 5, Analyzing Recursive Algorithms, the boss level.
I know mathematical recurrence relations can look incredibly intimidating to newcomers, but honestly, they are simply a systematic way to measure algorithms that call themselves. So the crucial point is understanding recursion, which is solving a larger problem by breaking it down into smaller, self-similar subproblems. Many of the most advanced, powerful techniques in computer science, like divide and conquer or dynamic programming, rely entirely on this single fundamental concept.
When you need to actually analyze the time complexity of a recursive algorithm, experts use a very specific three-step playbook. Step 1, identify your total input size and figure out exactly how many smaller subproblems you're creating. Step 2, write out the mathematical recurrence relation based on those subproblems. And step 3, solve that relation. You usually do this by drawing out a recursion tree level by level, or by using an incredibly powerful shortcut called the master theorem.
Now, what's really interesting about this slide is how we can decode this scary-looking master theorem formula into plain, empowering English. The equation looks wild, sure, but all it translates to is this. The total time of your algorithm, T of n, equals the number of subproblems you created, that's A, times the time it takes to solve each subproblem of a smaller size, that's n divided by B, plus whatever extra work you have to do to combine those smaller answers together at the very end. That's it. It's literally just a recipe for dividing up work.
Let's see this master theorem in action using merge sort. Merge sort divides an array into two halves, so our A is 2 and our B is 2. It then recursively sorts both of those halves. Finally, it takes a linear amount of extra work, O of n, to merge those sorted halves back together. So our recurrence relation perfectly matches our formula. T of n equals 2 times T of n over 2 plus Cn. When you plug that directly into the master theorem, it effortlessly spits out a final time complexity of O of n log n. See? The progressive disclosure of the math makes something highly complex suddenly feel quite intuitive.
And just like that, the developer's toolkit is now yours. We've gone on quite a journey in this explainer today. You now understand how to organize data sequentially or hierarchically. You know exactly how to measure the time and space a program consumes. You speak the asymptotic language of big O, theta, and omega. And you know how to break down the boss level of recursive algorithms using recurrence relations.
You are no longer just writing basic code. You are engineering highly scalable solutions. So my final question to you is this. With these powerful analytical tools now firmly in your hands, what massive, complex, real-world mess are you going to optimize first? Thank you so much for joining me on this explainer, and happy coding!